can't see it, you can't hear it, you can't weigh it, but we experience it every moment. The whole piece of time is a landscape, and we move through it, slice by slice. But do we really understand time? Is time same for everyone? To understand time, let's go back in time and make a small journey with a certain young patent clerk, Albert Einstein. Imagine you're traveling with Einstein in a train moving at a certain uniform speed. The train, relative to the outside environment, is in motion. The two of you sitting inside, on the other hand, observe each other as stationary objects, as both you and the train are moving at the same speed. Hence, relative to the train, you are stationary, and the laws of physics stay same inside the train as they would on the ground when you are standing still. Now, let's consider you get off the train and observe it moving across in front of you. Now, you are stationary, and relative to you, Einstein is moving with the same speed as the train. This is the phenomenon of relative motion, and we observe it every day. Does everything in the universe observe this relative motion the same way? Yes, everything except light. Light behaves in a different way. Imagine you have a light clock with you. This light clock has two mirrors in the opposite directions and a light beam bouncing between them. Now, let's say the distance between the two mirrors is d, and the time for the light to cover that distance is t. For the sake of simplicity, let's say it's 1 second. So, when this clock is with you at rest position, the light bounces between the mirrors, covering distance d in 1 second, which gives us the speed of light s. Now remember, speed is distance per unit time. Now consider Einstein also possesses the same light clock with him. Only this time, he's traveling in a spaceship along with the clock. When Einstein travels in a certain speed, the clock travels with the same speed of the spaceship in the same direction. Here, light has to travel an extra distance in the same 1 second. Let's consider this distance to be capital D and represent the speed of light here as capital S, which has to be greater than small s. But something's wrong here. Because in the late 1800s, the Michelson-Morley experiment tried to detect the relative motion of the matter through an ether and concluded that the speed of light is constant. This cosmic speed limit is known as c. So, in our little scenario, small s and capital S are equal. So, for the speed of light for both you and Einstein to remain constant, something has to give way. That something is time. It turns out, time slows down when you travel faster and faster, nearing the speed of light. So, the faster Einstein travels, slower the time passes for him. Hence, what could be a day for Einstein in space could be as much as 50 years for you on the ground. This became the fundamental conclusion of the theory of relativity, a theory proposed by Albert Einstein in 1905. This theory broke the traditional understanding of time as a constant entity and proved that time, in fact, is different for different observers. The theory of relativity led to many other invaluable findings, the most famous of which is the equation E equals mc squared. But more on that later.